Hello everybody, I'd like to welcome you here on my talk. And here on this talk I will talk about serverless and AWS Lambda and how Java bears with that. Because I think that many people still think, and in the past maybe it was true, that Java was slow on serverless and AWS Lambda, but it's no longer true. And maybe it wasn't even true. You'll see why. First, shortly about me, I'm Ondro Mihaly. I'm a Java champion, Czech Java user group lead. I'm also a committer on Jakarta EE specifications, a few of them. And I'm a director at Omnifish, which is a company that provides glassfish support and is tightly related to Jakarta EE. But let's start with AWS first. And their Lambda service. There are other cloud providers that have similar services, but I'll focus on AWS Lambda because it's basically more or less the same. There are similarities, but the basic idea is the same whether you use AWS Lambda or Azure functions or Google Cloud functions. And every time you have basically some life cycle like this. So the idea of Lambda or functions as a service is that you write some code and you just store it somewhere into the cloud, and the code is executed only when needed, and when it's not needed basically it just sits there. So in fact it uses resources, CPU, memory only when it's executed, not entirely, because it has to be also initialized sometimes before it can be executed. And then we have this life cycle that covers it. So most of the time, what you like to do is just process requests. So only this in the middle, this invoke stage. This is actually where the real work is done, processing some incoming event and creating some response. But when the code is not initialized, I have to be really close. When the code is not initialized, so it just sits there but is not used, it may not be warm. And by warm it means that it's ready to respond to the events. So when it's not warm, it's like hibernated, it has to be initialized first. And AWS Lambda has to create environment for it, basically a Docker container, whatever is underneath, we don't really know. And then it starts the JVM, and then your function is ready to serve requests or basically process the incoming event. And this whole process before your code is executed is called cold start or initialization phase. It consists of three basic steps. One is to load extensions for the environment, which is like monitoring, and a lot of cloud services can be attached to your environment. Then there is runtime, which is more or less something like a Docker container or operating system that runs the JVM in the end. And the last step is the JVM, in case of Java. In case of other language, it's a different language. So with Java we have JVM that needs to start, but then there's something more that can be done in this initialization phase, and that's basically static code initialization. Because before we get to the invoke phase, Amazon engine basically loads our code, loads our class, creates an object, and then it wants to call the method on the object. So calling a method on an object is basically this invoke phase. It's handling our request. But since the method has to be called on an object, you can even place something in a constructor or a static initializer block when the class is loaded, and this all happens in the initialization phase. So it's only called once, and then more requests can be processed with this object. And then the request processing is basically just a method call. We don't call this, it's a AWS infrastructure that creates all these and then calls our method. So we just basically care what is coming to the method as the event data, and then we run our code and output the event data. And at the end, sometime after, if our code is not used, maybe 10, 15 minutes, 30 minutes, when AWS infrastructure decides that it doesn't want to keep our code warm, it will hibernate it. So it will basically shut everything down, shut down extensions, shut down runtime, and then when there is a new event after some time, everything has to start again. So what I want to highlight is what I basically said, that the function part in the initialization phase and request is our code. In the runtime it includes Java startup, so JDK initialization and running our code, and running some AWS code, because it's Java code by AWS, then in the end loads our own class. But then we can start some processing in the initialization phase, in the static block, and then also in the request. So this is important when we realize that what we normally pay for is only for requests. So anything we put into the initialization block, to, for example, to establish a connection to a database or something that can be cached between multiple invocations, or read some configuration, it can be stored in a static object, and that can be done only in the when first time the Lambda is initialized. And this is our code, but Amazon basically runs it for free. They only charge us for running the code that processes events. But there is a catch. This only works for AWS supported runtimes. So if you use currently Java 8 or Java 11 runtimes provided by AWS, you have this benefit. If you use a custom runtime, if we, for example, want to run Java 17 or some other distribution, not Corretto, which is inside, or something, or you want to shrink the JVM with JLink to absolute minimum, you have to use your own custom runtime, and then it's the other way around. You pay even for the things that AWS does, or for all the initialization. So it really is important how long cold start is, not only because it delays your application processing when there is an incoming request and the Lambda is not prepared. It has to initialize, and it takes some time, and only then it can quickly process the request. So you can have 1 second delay, 5-second delay. It depends on how fast your Lambda initializes. And you either pay for it or Amazon pays for it. But yeah, most of the time, I would say you pay for it, because most of the time now you would like to use Java 17 and it's not supported by AWS Lambda right now. So, but in the end, it's not a big deal, because I don't have the numbers, but many people told me that this cold start doesn't happen so often. So if you pay some more money for this cold start, it doesn't make so much difference. But where it makes a difference is when you have user-facing processing and you want to process requests fast, and you can't afford that your Lambda takes a couple of seconds to initialize, and only after that starts processing requests. That can happen, like first request after night in the morning. First person that comes to use your application would have to wait a couple of seconds until this page loads. And the problem is if there is a chain of lambdas, so one lambda calls another lambda using some blocking ways, like a REST service, then this adds up. So you can have more and more lambda functions starting from cold start, and it can even grow into 20 seconds. So that's why blocking calls in Lambda are discouraged. Usually it's recommended to use asynchronous processing, so trigger an event, stop your Lambda, and respond with something, and then the other Lambda runs asynchronously. But that's just best practices. I'm not going to go deep. I want you to understand that Java is not worse than other languages, and actually the cold start with plain Java is not that bad. There are some measurements done by a guy on the internet. I don't know how valid they are, but I also consulted with some AWS engineers, and they told me that it's more or less like that, so it's not too off. And this guy compared startup times with very simple application, no framework, with all these languages supported by AWS. And Java actually was almost the same as any other language. And there was no language in particular like drastically faster. Python, you can see that is a bit faster, but even Java usually ran in or started in what is this, half a second. Or yes. So the problem in reality is not Java itself, is the frameworks and the way how we were used to develop and deploy our applications. I want to show you something for comparison. I have a few versions of the same application. All of them are based on Jakarta EE servlet, and it's basically just a simple server that gets an HTTP request and returns a response hello world from application. But they run on different Jakarta EE engines. And when we run the application on Glassfish server, which is a Jakarta EE full profile server, give me some time to launch it. I'll first launch it to show you what the application does, and then we'll just measure how fast it is. You can see it's not fast, but we don't have numbers. I will start a second time and we'll measure how long it takes. But basically, the output is, I think it's not on the same on this URL. What is the URL? Simple app. Oh. So just hello from Glassfish. Very simple, simplistic application, but even that takes a couple of seconds to load, basically. I have a command to measure how fast it is to start Glassfish server, deploy the application, and serve the first request. Because even if you even if you serve the request for the first request, it still may load some things. So I want to measure everything, because some runtimes initialize things and then initialize some things later when there is a first request. So I want to really measure the real situation and the time needed for everything to load. So I have a script to measure it, and with Glassfish this application is ready to serve the request in 4.3 seconds. Not that bad, since it's a whole application server, although it's just a servlet that it needs to run. But I have a chart here, and let's record it here in this chart. This chart shows different runtimes and how long that takes. So this one is 4 seconds. The first one is for Glassfish. I think I can full screen. Yes, so it's bigger. And just remember that it's the first measurement. But I have another variant of this, and it's again Glassfish, but Glassfish embedded, which means it runs with only the necessary things to run our application. No administration console, no serious, or there is serious stuff, but it doesn't load the unnecessary stuff. And in this case, again, the same application, but it takes 2.5 seconds to start. So we got slight improvement. Actually, almost half the time went off. You can see the difference here. Then let's try Spring Boot application, just to see how the Jakarta EE competition works. It's again servlet, because Spring Boot supports Jakarta servlet, so I just ported the same servlet to the Spring Boot application. We have this command, run it, Oh, I think it occupies the board. Something left running. Let's see. Yes. So actually Spring Boot does a pretty good job again. Roughly half the time off compared to Glassfish Embedded. So we're slightly improving. This is the Java ecosystem. The power of Java is that every time there is something that improves and we don't have to change much in our applications. Sometimes. Okay, but that's not the fastest that Java can do. When we run just very simple Java, you know what it does? It doesn't do anything almost. No. Oh, where's the code? Okay, so I'll open this. It's as simple as that. Just system out print line text. But when we run it, we'll see that caps lock. Caps lock doesn't like me. Oh wow. Not even 100 milliseconds. So can we compare it even? So this is how fast Java can be. Just 50 milliseconds to print something. I know it's not a lot. It's very small program, but we can now compare it with a binary that can do it. Like, and which language can be faster? That it doesn't even make sense to try to be faster than 50 milliseconds to start. But then we need to add something on top of it. So we will make the startup time longer when we add some functionality. Now, would we use anything like this on the left, Spring Boot or Glassfish or anything like that? There are other options. We want to get as close to these plain Java startup times as possible. And there are two frameworks I'd like to show you very briefly now that try to achieve that and more or less succeed, each of them in a different way. One of them is Quarkus framework. If you probably noticed some presentations that already explain what it is, but in short, it's based on Jakarta EE and microprofile specifications, not all of them, but it contains pieces of those. It is built on some existing frameworks or libraries like REST-DZ or Vertex, but it also redesigned the dependency injection with its own dependency injection implementation. And this dependency injection implementation, this ARC, is at the core of the whole framework, because it supports ahead of time optimizations. So it's not still compilation. We'll get there quickly. But it is able to improve the bytecode or generate bytecode that is tailored to your application. So instead of processing annotations, instead of dynamically loading your dependencies and injecting them into your code, it actually generates the bytecode that does it directly. So it's basically the most optimal way, because you can, it's like if you've written the code directly, like a variable equals new objects, almost like that. No injection, like trying to find which object can be injected, what is the type of it, which object matches. No, this is the simplest possible way. But it's generated based on the source code that you already know with add inject. So the metadata is there, but is not processed during runtime, but pre-compiled. Then there are many plugins that supports this way of working and support some AOT optimizations, and also prepare that there's another part of Quarkus. These libraries make it possible then to gather some metadata and like modify the code so that it can be compiled using GraalVM into native binary. So that's another thing that Quarkus supports. That's an optimization we could use, but I want to focus on in this talk on plain Java, and then we can briefly touch with GraalVM what is possible and where it makes sense. It also supports imperative and reactive programming. You can choose any of them if you like reactive programming. But what is important with Quarkus is it optimizes the startup time and also tries to shrink the size of your application because it does some ahead of time or build time optimizations. So the resulting binary can be different than if you just compile it and assemble it using Maven. Another option would be Piranha Cloud. You probably haven't heard about it, it's not so widely used. But it has a different approach. It starts with a very small and efficient servlet container written from scratch. Uses flat class path, so no vars, no class loader hierarchies. You can basically load everything from the class path. Some features work only if you wrap your code into one class loader, so that's like easy to find out what's in your application, to find out all the annotations or all the resources. But it's also possible to do that on the flat class path. It's just not so straightforward. And then it adds existing components, mostly from a Glassfish server, but it also takes some useful things from others. What is nice about Piranha is that it's really fast. The servlet container is really fast. It starts maybe even faster than Quarkus. And then it's extremely modular and extensible, and it builds natively on Jakarta EE. So it provides Jakarta EE distributions, not completely, because it's still a small framework. It doesn't support all the Jakarta EE APIs, but it's slowly growing, and slowly things are migrated from Glassfish or from other libraries, or libraries are supported, so that it adds better support for Jakarta EE, and the aim is to support Jakarta EE web profile eventually. First core profile, which is almost there, and web profile eventually in the future. And it supports a lot of other plugins. But what is nice, you can really assemble everything from your own. It's like Lego, you can just pick small things. And an example of that, I will show you some source code of a sample project. An example of how extensible and how modular Piranha is no, not this one. Is that you can assemble the servlet container without the HTTP listener, so you can use it as an engine, embedded engine. You create an object like this. You can create embedded request, which is an object created by you. You can add any HTTP data there to simulate the HTTP request, and then you get the response, which is again an object. So in some cases you don't need HTTP listener when the requests don't come through HTTP directly, or you just want to use this engine to generate HTML based on JSF, but then do something else, then send it to a browser. You want to use it as a templating engine or something like that. So this is also possible, because you don't rely on having the HTTP stack, and it doesn't make sense to have HTTP listener if you want to just process some resources internally. So the simplest code with Piranha would be like this. You configure the Piranha at the servlet, standard Jakarta EE servlet. Then you create a request just to trigger the servlet. If you map it to the slash context root, then you don't need to do anything, because this is the default. And then you get response as a string, and you can print it in this case. So in this case, basically, the servlet is invoked and hello from Piranha Cloud is printed. But if you want you can add, where is it? You can add the HTTP server and add Piranha to it. So it would, the HTTP server would delegate to Piranha, and this is like 2 layers. You can exchange different HTTP server implementations with the same Piranha core servlet engine. So you can choose which one. There is one implementation for Project Loom for virtual threads, which just spawns a new thread for every request and calls Piranha to process the request. So you can even write easily your own servlet engine and put Piranha into it. So this is quite nice example, I think. And then when we get to serverless, imagine in serverless you basically don't need HTTP listener, because in AWS Lambda, what AWS Lambda does, if you remember what I said, it just calls a method. So let's see how it looks like. This is an example. I should have made it bigger. So this is an example in a different way how you can use or call Piranha. This is the same thing. You create Piranha, add a servlet to it, and start. And if you closely look at this, this is in the static block. So it's not in a block, it's just initializer of a static variable, so that you can access this Piranha engine later. But this is static, so this is called only when there is a cold start initialization. And then every time there is an event coming, only this method is called. And this method gets an object. In this case, it's an object of type API gateway, a request. So if the request comes through API gateway, which is basically the HTTP listener in AWS infrastructure, it delegates in this way, it delegates to your Lambda, and your Lambda can delegate to Piranha by creating the request, mapping all the data from this AWS object into the Piranha object, and then call Piranha to service this. So this is how you can use Piranha without any magic, with just small amount of code to process a request in AWS Lambda with standards. So this doesn't make sense to do it on a very simple Lambda like this. But if you have already existing servlets that do some things, or things that run on servlets like Jersey or something like that, you can deploy it on Piranha and then embed it into your Lambda function. Okay, so there's some more things I'd like to show you. It's not only about choosing the framework. So with the framework, I forgot to show you how fast it is. So sorry for that. I want to also show you how fast Piranha is. That's the thing that I forgot. Piranha app. So this is again the same application. It starts the servlet and we'll measure again. And this time 150 milliseconds. This is the time it takes Piranha to load the servlet and process the request, the HTTP request, and produce a response, including start. So if we put it into the chart, you see it's much closer to the Java start time than to the startup times of any other runtime. So it's up to you. We can talk after the session if it's enough or if it makes sense, or you don't believe that. We can discuss. Obviously, if you add more, like Jersey, or more functionality, more components, you get to longer startup times, around a second. So then it slowly gets to Spring Boot, but it's still faster, and that can be optimized in the future because it's just plain Java. Okay. So how did I do this? sorry, I want to start the presentation again. Need to restart. Let's see where we were. Okay. So that was about frameworks. So if we improve the runtime that runs our code, we can get much faster startup times. There are other ways how we can improve the startup times, and this is an example of my own measurements. It's not really science. I tweaked with some JVM options and measured. I ran every time the code 5 times, and it was just, I think in this case I used Quarkus, which serves again a very simple REST request. And you can see on the left there are various Java options that I used, and on the right we have 2 Java 11 distributions, 2 Java 17 distributions. This is not AWS Lambda. This is on my computer. In AWS Lambda, the numbers would be different, but the ratios would be roughly the same, I guess. And I used Corretto because Corretto is used in AWS Lambda as in the supported Java runtimes. So I used it as a reference. And we can see that there are 2 places where we can see quite a lot of improvement. Others either don't improve startup times or even make it worse. But this one, the 3rd line, and this one, CDS, and then combined, of course, CDS with something, improves the startup time a lot. Why? This first thing, tired stop at level 1, means that just-in-time compiler second phase is disabled. So it's not like just-in-time compiler doesn't optimize the code as well as it could, but it improves startup time because it already optimizes in the first phase and then just keeps the code running. It doesn't slow down our startup time. And you see that the improvement is roughly 10–15%. Another one is CDS, class data sharing, which means you have to start your application once, collect information which classes were loaded, and the metadata about it, and the JVM will store it into a file, and the next time you can use this stored file to run your application faster, and it actually is quite a lot faster. It's faster, in this case, about 25%. So and you can combine those. Another thing that stands out is particularly this Zulu Java 17, which is for some reason faster than any other option. So I don't know why, but this is just shows that even distributions of the same Java version can have different performance. I don't know why, how they do it. Maybe they enable some optimizations by default or compile some things in a different way. But it's worth to consider. There are other things that you can do to optimize Java. I don't have time to go through them, but one interesting thing that I didn't mention is shrinking down the JVM with JLink just for your application. You can remove the classes that your application doesn't need, and you get a smaller JVM that's faster to start. And then you have native binary, which I mentioned. The Quarkus tries to support it natively. There are still some limitations, but it does a good job there. There are other frameworks that try to also support it, like Spring Boot is going to support it natively soon. Piranha doesn't support it, just you can try, some application will work, some probably not. What it does, it basically compiles a binary, like from a C code you get a binary, and then you have a very fast thing. The disadvantage is that build time is much longer. It can go up to hours, and then you have a completely different sort of issues because not JVM, it's compiled code, so you can have things that you didn't discover while coding in JVM. So yeah, conclusions, I hope that you get it yourself. Basically, what I wanted to say is you have to rethink if you already thought that Java is fast. I'm saying it's not Java. It's the way how we use Java, and we can find ways how to improve that, or find runtimes that are faster, or approaches that lead to faster code, at least faster to start. Do you have any questions? If we have some time for questions. Okay.
Thank you. So, I didn't know about Piranha, which I believe is a recent project, but I think there are other similar web servers you could easily embed in your application. I did something with Jetty in the past. So what are the advantages of Piranha over Jetty, for example?
Yep, so one advantage of Piranha is that it's completely embedded and simple. With Jetty, you can embed it, but it's an embeddable server, but basically you have to deploy applications onto it. Like, maybe I'm wrong, so we can talk later. Yeah. But I think it's not as fast, because Piranha is very rewritten from scratch. Only was necessary based on the class path. Maybe I have to look into Jetty, the new version of Jetty, if it's as fast.
No? Netty would be the same, I guess. No, you can.
Netty is not the same, because Netty is not a Jakarta Serverless framework. It's just a networking framework. You would have to add a lot more on top of it. With another thing with Piranha is that it supports servlets as well as Jetty, but it also has its own ecosystem of integrations and extensions, so you can create a runtime that supports more than just servlet. You can get REST by adding the Jersey extension to it, and basically it's really optimized for making it easy to embed and easy to use and fast startup times. But I admit Jetty may be good as well. It's just Jetty is just Jetty, and there is no ecosystem around it other than servlet and things like that. But maybe I'm wrong. Maybe I'm biased. But I look at Piranha like a year ago, and I really liked it. And it's not entirely new. It's like 3 years old. It's just it doesn't get so much adoption, and it's still like work in progress.
Thank you.
I think it's interesting, so I recommend to give it a try and have a look at this. I think we don't have more time, so thank you for coming to my talk, and thank you for the question. If you want to have a T-shirt, I have a few here, so stop by and we can talk more. Goodbye.